Hi, my name is dr. Ahmath. Welcome to this lecture 7.1. Today we're going to discuss about the normal distributions, and we're going to discuss how to calculate the probabilities associated with the normal distributions. So I would like to show you a couple of examples of the discrete normal distribution, or discrete version of the normal distribution, so called binomial distribution. If you remember, you've got the random variable which has the binomial distribution, and it's going to have the mass function like this. Or if you go through the grades after the exam, you usually have this kind of distribution of the grades. So essentially, this graph tells us that there are a lot of people have got the grades in the range between 51 and 60. So you can see here the ranges here on the bottom, and not so many people have got the grades between 11 and 20, and not so many people have got the grades between 91 and 100. So we call the distribution as normal when a lot of people will get the grades, or a lot of occurrences of your random variable are going to be around the mean. And as far as we are going to go far away from the mean, the frequencies are going to be slower. So this is what we call as a normal distribution. So a continuous probability distribution that is symmetric about the mean. You can see here that this curve is going symmetrically around the mean, and also showing that the data is more frequent near the mean. And as far as we go from the mean, the frequency is going to be lower and lower. It's called the normal distribution, or sometimes we call this as a Gaussian distribution. So this is what is the definition of the normal distribution, and let us define what is its density function. So the density function of a normal distribution with the mean mu and the standard deviation sigma is going to be given like this complicated function. So the normal distribution is given with the two parameter, the mean of the random variable and the standard deviation of the random variable, and the density function is going to be given like this function. So what I want to do is I would like to play with this graph to try to understand how the mean and the standard deviation is going to change the shape of its curve. So sometimes we call the normal distribution as the bell-shaped curve as well, because it looks like as a bell. And if you remember, the density function is not the probability right immediately, but it's proportional to the probability. And you can see here that at the mean, so it's going to be the highest point always. So the probability, or which is the frequency, is the highest. As far as we go away from the mean, the frequencies or the probabilities are going to be lower and lower, right? And it's symmetric. So what I wanted to try to understand is, I would like to try to understand how, if I change the mean, so the shape is going to be changed, and how if I change the sigma, the shape is going to be changed. So I'm going to use the application which is called like a GeoGebra. So here I just drew this function for the mu is equal to the 0 and sigma is equal to the 1. So maybe you already understood this, how it is going to change from the transformations of the function. So here, what I'm doing with the x is that I'm subtracting the mean from the x, right? So if you subtract some constant from the x, so your curve is going to move in the horizontal direction. So for example, if I just change the mean to the 1 or to the -1, you can see here that the curve is simply moving. Okay, so if I go to the 1, so it will just go to the 1. If I go to the -1, the highest point, -1.4, the highest point of the curve is going to be at the -1.4. But you can see here that it is not going to be the flattened if you change the mean. And rather, if I go to the mean to be equal to the 0 now, and if I play with the sigma, so here the sigma, the standard deviation is given to be equal to the 1. So what do you think if I just increase the standard deviation, so how the shape is going to be changed? So increasing standard deviation means that the points are going to be more far away from the mean in general, right? So if I just increase the standard deviations, you can see that here that the curve is going to be more flat. And if I decrease the standard deviation, like 0.5, for example, which is going to be a little bit sharp. Okay, so this is how the mean and the standard deviation are going to change the shape of this curve. Cool. So there is a special case with the normal distribution, which is called like a standard normal distribution. So the variable z is called a standard normal distribution if the mean is equal to the 0 and standard deviation is equal to the 1. So this is the special case, and it is very useful case because just using this case, we're going to evaluate lots of probabilities. So here, the mu should be equal to the 0, and the sigma should be equal to the 1 here and 1 here. So if I substitute sigma was equal with 1 and mu was 0, then simplify this term, I'm going to get simply this kind of function. So this is going to be the density function of the standard normal distribution. And what we're going to do is we are going to consider a couple of examples of calculating, of evaluating the probabilities associated with the standard normal distribution. So the standard normal distribution is nothing else as the just the particular case of the normal distribution when the mean is equal to the 0 and standard deviation is equal to the 1. Okay, so let's do an example. So let's say a company produces the thermometers which measures 0 degrees at Celsius when the water freezes. But again, so not all of the thermometers are good enough. So some are going to measure a temperature less than 0 at the same when it is actual 0. Or some of the thermometers are going to measure the temperature above the 0 when the water freezes. Okay, so they have some error. So what we wanted to do is but if I just test this for lots of thermometers, so in average, the temperature at the freezing water is measured to be equal to the 0 degrees. Was the standard deviation 1 degrees. So which is kind of the standard normal distribution, right? If we assume that the measurements of the thermometers have the normal distribution with the mean to be equal to the 0 and standard deviation to be equal to the 1, then this is going to be simply the standard normal distribution. So now what I wanted to do is I would like to choose one of the thermometers randomly. Okay, and I would like to know what is the probability that the reading on that thermometer is going to be show the temperature less than 0. Okay, so what I have to do is I need to just draw the curve of the standard normal distribution, and if I know I should know that the mean is equal to the 0, right? It's the highest point. And what I have to do is I need to find the area up to 0, because this is what I have to do. So I need to find the probability of the z is smaller than 0, right? And if you remember, it is going to be done by integrating the density function from minus infinity to the 0. So graphically, it is going to look like this. So we have to find the area up to this point. And please note that this curve is completely symmetric around the mean. Okay, so that is why the area lefter than the mean is going to be the same as the area which is more righter. Okay, so this area, so let me denote this as the x, it is going to be the same as this area x. So we know that the sum of all of the areas under this curve should be equal to the 1, right? From here, it is clear that x is equal to the 0.5. So the probability that randomly chosen thermometer is going to show a temperature less than 0 degrees is going to be equal to the 50%, or 0.5. So what if we are given the temperatures like not 0, so some other values of the z? So what if so I would like to choose a thermometer and I would like to know the probability that the thermometer is going to show me the value less than 1.27 degrees, right? So in this case, I have to find the value, right, of the probability of z is less than 1.27, okay? So I have to actually integrate the density function of the standard normal distribution from minus infinity up to 1.27. But fortunately for us, people have integrated this function numerically with computers for many values of the z. So including 1.27, and what we have to do is we need to look this from the table. Before we do this, we have to introduce something which is called a cumulative standard normal distribution function, phi of z, which is the area under standard normal distribution curve up to some point z. Okay, so phi of z is going to give you the area until the z. For example, if you choose z to be equal to minus 1, then the phi of 1 is going to be this area up to minus 1. So this is going to be phi of minus 1. So if you would like to choose the area, for example, up after minus 3, for example, plus 3, right? If you would like to find this area area is going to be 1 minus phi of 3, because the phi of 3 is the area up to 3, and the area after 3 is going to be equal to the 1 minus the area up to 3. Right? So this function is very important, and it appears that lots of values of this function is given using the table. So if you open actually any book on probability or statistics, you can find this table at the end of your book. So we are going to discuss how we need to use this table. So this table is going to given you as a two-dimensional array. Okay, so if we need to find a value of the phi for the 1.27, right? So we have to find the value of the phi for 1.27. So we need to find a value from the first column, which is going to be 1.2. Okay, then we need to find the corresponding value from the first row, 0.07. And I'm choosing these two values because the sum of the 1.2 and 0.07 is going to give me exactly 1.27. Okay, so the 1.2 plus 0.07 is it 1.227. Okay, so actually this 1.27 is split into the two parts, and you have to combine them, or you have to find the parts of 1.27 from the first column and from the first row. And the value which is going to be in the intersection of that at the particular row and at the particular column is going to be the value of the phi. So I'm going to do this. So I'm going to go to that row where the 1.2 is located, and then I'm going to go to the column where the 0.07 is located, and the intersection is going to be 0.8980, which is the value of the phi. So which is the area up to 1.27. So the probability that if I choose one of the thermometers randomly and its value is going to be less than 1.27 is going to be 0.89 and 80. Okay, so this is how we are going to evaluate the probabilities for the standard normal distribution just using this table. So I'm going to do a couple of exercises on this. So another exercise is going to be also associated with the same problem which we're solving. So now let's say I'm going to choose one of the thermometers. What is the probability that its measurement is going to be below the -2? So again, I'm going to draw the curve for the standard normal distribution, and I'm going to sketch the -2. So actually, it is not absolutely problem to find this, again, phi of -2 in many cases, but the problem is for many books, you are given the values of the phi for the positive values of the z. So the phi of z you will be given for only z is positive. Okay, while if you need phi of -2, you have to use the value of the phi of t, for example, in order to find this. So since this curve is completely symmetric, it appears the area up to -2, it is going to be the same as the area after 2. So these two areas on the tails of this curve are the same. And we're going to use this fact in order to find the probability of z is less than -2, or the cumulative area up to -2. So we're going to find the cumulative area up to 2, and we're going to subtract this from the 1 in order to find the cumulative area after the 2. And this is going to be the same as the cumulative area up to -2. So let's do this. So again, I'm going to use the table. So from this table, so I'm going to split this 2 into the two parts again. So what I have to do is 2.0 plus 0.00 is going to be 2.0, right? So I need to go to this column, 0.0, and to this row. So the row is going to be there, a little bit down there. So at the 2, so let's do this. So I need to choose this column, then I need to go to the 2, and that's going to be its value, 0.9772. So this is the area up to 2. So this is pi of 2. So if I need to find the area after the 2, I have to subtract this from the 1, and this is what I'm going to do. So if z has the standard normal distribution, and phi is the cumulative standard normal distribution, right? So phi is going to give you the values up to the area under the standard normal distribution curve up to that particular z, then phi of minus z can be found as subtracting phi of z from the 1. So, and in particular, phi of minus t is going to be 1 minus phi of t. So we've already found that the phi of t is equal to the 0.9770t, and if you subtract this from the 1, it is going to be 0.0228. So the probability that a randomly chosen thermometer is going to show a temperature below the minus t is going to be 0.0228. Okay, so let's do one more exercise when we have to find the probabilities in between the t values. So now let's say that I need to find the probability that the randomly chosen thermometer is going to show me the temperature between minus t and 1.27. So in this case, again, I have to use the function phi, so essentially cumulative distribution table. So in order to find the area in between, what I can do is I can find the area up to here, which is like a phi of 1.27. Then I can find the area up to here, which is like a phi of minus t. Then I need to subtract them, right? Their difference is going to give me the area in between of them. And we've already calculated phi of 1.27, which was 0.89 and 80, right? And we've already calculated phi of minus t, which was 0.0228. We just need to subtract them in order to find the probability in between these two numbers. So this is how it is going to work always. So if you need to find a probability for the standard normal distribution curve, for the standard normal distribution random variable, and between the t values, you just need to find a phi for these t values and subtract them. Okay? So we're going to subtract this, and this is going to be 0.8750t. Okay? But the problem is, most of the time we are given normal distribution, not the standard normal distribution, and how we need to learn how to calculate the normal distributions. The thing is, standard normal distribution is always unique. It is the normal distribution with the mean 0, and the standard deviation is equal to 1. But in general, the normal distribution can have any mean and any standard deviation, right? So we can't really just make the tables for all of the values of the mean and all of the values of the sigma. Because, for example, I can say here that the distribution of the final grades after the midterm, after this semester, has the normal distribution with the mean 57. Or, for example, distribution of the midterm grades have normal distribution was the mean like a 42.9, right? We can't really just make the tables for all of the values of the mean because there are infinitely many values. So rather we have to learn how to calculate the normal distribution using the standard normal distribution. And it appears it is possible to do this. So let's try to solve this problem. So you know that typical height of the home doors is 2 meters. So given that heights of men typically have normal distribution with the mean 1.75.2 meters and standard deviation 7.11 centimeters, what is the percentage of the men who cannot fit to this door without bending or bumping their heads? Okay, so we assume that the distribution of the heights of men have the normal distribution with the mean 1.75.2, right? So what we need to do is we need to find the probability that the randomly chosen man is going to have the height more than 200 centimeters. So this is going to give you a percentage of the men who cannot pass through these doors, actually. So we don't know how to calculate the normal distributions, right? We don't know how to calculate the probabilities associated with the normal distribution, but we know how to do this with the standard normal distribution. So it appears it is possible to transform the normal distribution into the standard normal distribution using the following formula. So if you're given the normal distribution with the mean mu and standard deviation sigma, then its corresponding standard score, or z-score we call this, is going to be obtained by subtracting the mean from the x and dividing this to the sigma. Okay, so I'm going to explain this in a moment. So just remember this formula. So this is called as the z-score. Okay, so for example, if you have to find the area up to 200 centimeters, when the mean is 175.2 and the standard deviation 7.11, so you're going to make this like this. So its corresponding z-score is going to be, so x is 200, minus mean is 175.2, divided to the 7.11 is going to be its corresponding z-score. So this is how we're going to calculate the z-score. So when we calculate the z-score, we can find the probabilities for the z, for the standard normal distribution, right, from the table. Okay. So let's do this. So we have to find the probability that x is smaller than 200, first of all, because we know that phi, the cumulative standard distributions, are given up to some point, right? So I'm going to subtract the mean and divide this to the sigma from both of the parts of this equality. So if you subtract the mean and divide this to the sigma for the x, it is going to be x minus mean divided to the sigma. And for the 200, it's going to be 200 minus 175.2 divided to the 7.11. So I'm going to simplify this term. So you know that this formula is nothing else as the z, right? And I'm just going to substitute this with the z. So it's going to be a probability of z less than 3.48. I know how to calculate this. This is going to be phi of 3.48, right? Oh, oops, it should be phi of 3.48. And I can go to the table and find a value of the phi of 3.48. And this is going to be 0.9997. So please note that if you would like to find a probability that x is greater than 200, right? So it is going to be equal to the 0.0003. Okay, so actually, only 0.03% of the males cannot go through these doors. So it's really tiny percentage. So it's totally safe to make the height of the doors to be equal to the 200 centimeters. So let's do a couple of problems on calculating the normal distributions using the standard normal distributions. So it appears the birth weights in United States have normal distribution with the mean 3,420 grams and the standard deviation 495 grams. So in one of the hospitals, in Newport General Hospital, requires special treatment for babies which are less than 2,450 grams, which is called like unusual, and greater than 4,390 grams. So what is the percentage of the babies whose weights are in between these two values who do not need a special treatment? So what we need to do is we need to find a probability that the randomly chosen newborn baby has the weight in between these two values. So in order to do this, we have to first of all calculate the z-score for each of these values. So the z-score of the 2,450 is going to be, so 2,450 minus 3,420 divided to the standard deviation, which is 495. And if you calculate it, it's going to be minus 1.96. And the z-score for the mean, actually, it's going to be simply 0, right? Because you subtract the mean, it's going to be 0. So z-score for the 4,390, it's going to be 4,390 minus 3,420 divided to the 495, it's going to be 1.96. So what we have to do is we need to go to the table, cumulative standard normal distribution table, and find the probabilities. Okay, so the probability that x is between 2,450 and 4,390 is the same as the probability of the z is between minus 1.96 and 1.96. And it is equal to the phi of 1.96. It's the area up to 1.96 minus the area up to minus 1.96. So if you go to the table and you can find that the area up to 1.96 is going to be 0.975. It is the area starting from the minus infinity up to there. And the area until here, until minus 1.96, it's going to be 0.025. And the area in between is going to be 0.25. Which basically means that roughly 95% of babies do not need a special treatment because they fall into this weights in between 2,450 grams and 4,390 grams. So this is what is called a normal distribution. The normal distributions are superbly important in our lives because many things, many random phenomena around us can be explained using the normal distribution. And being able to calculate this is very important. Thank you very much for your attention. I hope that this was helpful for you.